folks. Let's talk about negative exponents, shall we? Got a definition for you. A to the negative n power is equivalent to 1 over a to the n. Now, that's a rule that basically says if you have a negative exponent, it belongs on the other side of the fraction bar. But I do want to discuss why real quick. So if I give you an example like x squared over x to the fifth, if we use the rules that we learned earlier about when you divide exponents, if you just subtract, now earlier what we did was subtract the bigger number minus the smaller number and leave the bigger one where it is. So if I do that, that's going to be 1 over x to the third. I realize that, and that is correct. But what if we just subtract the top one minus the bottom one anyway? Is that wrong? Well, that would give me x to the 2 minus 5, which is x to the negative 3. Aha! So now we've got this negative exponent, but I know it's supposed to be equivalent to this. Therefore, a negative exponent means you take that base to the other side of the fraction bar and change the sign of the exponent. So when you have down here 2 to the negative fourth, that's equivalent to 1 over 2 to the positive 4. They are the same thing. We are not talking about negative numbers, people. These are not negative value numbers. This is a negative exponent, and a negative exponent is just telling you to do something. It's like an operation. It's telling you it belongs on the other side of the fraction bar. Now, if I simplify this 1 over 2 to the fourth to the lowest terms, that would be, or completely simplified, you know, 2 to the fourth is 16, and that's complete. Next problem, again, this is not a negative number. This is telling you that the exponent is negative, which means it belongs on the other side of the fraction bar. And 10 to the fifth, you should know this, 10 to the fifth is a 1 with 5 zeros. So 1, 2, 3, 4, 5, and I go mark it off. So 1 over 100,000. Now this is weird. You know, if it was in the numerator, it went in the denominator. Well, hey, if it's in the denominator, it goes up to the numerator. So this will be 1, because it's already up there, times p to the positive 8. And then 1 times anything is that thing. So this is just p to the positive 8. Same thing here. Negative exponent means that you got to do something. It belongs on the other side of the fraction bar. So this will be the 1 that's already in the numerator, times 4 to the positive 3. Well, 1 times anything is that thing, 4 to the positive 3, and 4 times 4 times 4 is 64. So that's completely simplified. Now this is a fun rule. If you have a fraction raised to a negative exponent, so notice we have a over b to the negative n. Look what happened. When I go from here to the answer, the a over b flipped upside down to b over a, and the negative n disappeared to a positive n. So this is equivalent to b over a to the n power. Let's talk about why though, okay? So let's just say we have 2/3 to the negative 3 power. Now if I use the definition on the previous page, that means this is 1 over 2/3 to the positive 3, right? But now, whenever you, well, let's keep simplifying, okay? So this is 1 over, then we learned a rule a few sections ago that whenever you have an exponent outside a fraction, that applies to both of these. So this is 2 to the third over 3 to the third. But then when you have a number divided by a fraction, you flip the fraction. So this turns into 3 to the third over 2 to the third times that 1 that's already up there. That can be written as 3 halves to the third. So if you go from here to here, that's basically what this rule is saying. Without all those steps in the middle, you can save yourself about 4 steps. So look at the first example. I didn't even realize I was doing the same exact example. So if we use the rule this time instead of all those steps I used, this just means this is 3 halves to the 3 power, and then that would be 3 to the third over 2 to the third. 3 to the third is 3 times 3 times 3 is 27. 2 to the third is 2 times 2 times 2, which is 8, and we're finished with that problem. Here, again, you can apply the negative 2 to everything right now. My advice is to flip this fraction first. So this is y divided by negative 6x to the positive 2 power. Then apply the 2 to everything. So this would be y to the second. Now negative 6 to the second is 36, right? Because it's negative 6 times negative 6. And x to the second is x squared. So that is completely simplified. Now watch this craziness right here. Listen, the negative 2 only applies to the 4. Okay? Not to the negative 4, because this is not in parentheses. Look at h. H would be, it applies to the negative 4. So I'm going to apply the negative 2 to the 4 only, which means the negative stays in front, and this is 1 over 4 to the second power. Okay, so again, the negative came down, and then I handled just this, which is 1 over 4 to the second. And then this is going to be negative 1 over 16, and that's simplified. On the other hand, for h, because this entire negative 4 is raised to the negative 2, that means this is 1 over negative 4 to the positive 2. Now, negative 4 squared is negative 4 times negative 4, that's 16, so the final answer is 1 over positive 16. All right, got some more examples. Now look, I've thrown in some multiplication. So again, this negative 2 only applies to the 3, so the 5 stays where it is. And this 3 to the negative 2 is 1 over 3 to the positive 2. And you can think about this as 5 over 1. So 5 times 1 is 5. And 1 times 3 squared is 1 times 9, which is 9. So 5/9 is my final answer there. On the other hand, this next one is 5 times 3 to the, all of that to the negative 2. Well, y'all, you can go ahead and do 5 times 3. That's 15 to the negative 2. Which is 1 over 15 squared, which is going to be 1 over, and you know 15 squared is 15 times 15, which is 225. That's completely simplified. Next one, k to the negative 5. You know the rule, negative exponent means it belongs on the other side of the fraction bar. That's 1 over k to the 5th, and that's all we can do. And then now we have one where we have a power to a power. So you multiply those guys together, so that's z to the negative 21, right? But when I handle the negative exponent, that's 1 over z to the 21st. Now you might have been thinking, do I handle the negative exponent first? Sure, that's fine. That will give you 1 over z to the 3rd to the positive 7. Then you can multiply to get 1 over z to the 21. Either way. They're both directions are right. Let's continue with example M. Now this negative 1 only applies to the y. So the 6 stays in the numerator, and the y to the first goes in the denominator. Remember, when you move it to the denominator, the sign changes, and that's just 6 over y. All right, 6 times y to the negative 1. Here we go again. The negative 1 this time applies to the 6 and the y. So that would be 1 over, parentheses, 6y to the first. Well, that 1 applies to both of those, so essentially that's just 1 over 6y. Notice the difference between those. They look very similar, but it's a different result. All right, now, once again, we have only slight change. All of this is to the negative 1 power, so we handle that first. That's going to be 1 over negative 6y to the positive 1. Now anything to the positive 1 is just itself. That's 1 over negative 6y. We really shouldn't leave negatives in the denominator. This positive divided by a negative is overall a negative, so negative 1 over 6y is a better simplified result. Example P, x to the negative 4 times x to the 9th. This, to change to a positive exponent, means it belongs in the denominator. So we have x to the 9th over x to the 4th. But then, remember, when you divide, you subtract the exponent. So 9 minus 4 is x to the 5th. Now, some of you maybe didn't think about it that way. What if you thought about when you multiply bases, you just add the exponents? So that'd be x to the negative 4 plus 9, which is also x to the 5th. So notice it's kind of forgiving. As long as you use the rules correctly, what you do first matters less. What you do properly is what's important. So if we applied that to this next problem, all right, negative 3 and a positive 2, they're common base, which means you can add. This would be y to the negative 3 plus 2, right? Which would be y to the negative 1. And to write that as a positive exponent, that would be 1 over y to the first, which is really just 1 over y. Or, not both, but just or, you could say, hey, I got a negative exponent, let's make it positive. So the y squared stays on top, the y to the third stays on the bottom, and you all know that's 1 over y that way too. So you don't have to go both directions, but either direction you see is correct. All right, let's keep going. Now notice they have a common base of z. So I have two choices. I can handling each of these negatives first, or I could use my property that says when you multiply your bases, you add those together. Let's do that. Might be one less step. Negative 4 plus a negative 7. Careful with your signs. Negative 4 plus a negative 7 is a negative 11. And then to make that exponent positive, that means this whole thing belongs in the denominator. So 1 over z to the positive 11 power. All right. Here, notice we don't have any exponents on the outside of our parentheses. So that means it's time to go ahead and multiply. 3 times negative 4 is negative 12. U to the negative 3 times u to the second, we add those. I'm going to write that down so you can see it. That's u to the negative 3 plus 2. I have v to the 6 times v to the negative 4, so that's going to be v to the 6 plus a negative 4. So be real careful with your signs. So I've got negative 12, and when I add my u's, exponents, negative 3 plus 2, or negative 3 plus 2 is negative 1. When I add my v exponent, 6 plus negative 4 is 2. Then you look to see what belongs on the other side of the fraction bar, and it's only the u to the negative 1. So they have negative 12 v squared over u to the first. The negative can go in front of the fraction, because a negative divided by a positive is a negative. And the u to the first can be written as u. So negative 12 v squared over u. Final answer. Example T. Now notice here we've got a set of parentheses with an exponent on the outside. Remember that exponent applies to the 6 and the k to the negative 3. So let's write that down. 6 to the second. Also k to the negative 3 is raised to the second. Now you all know 6 to the second is of course 36. But now you have a power to a power, you must multiply. That's k to the negative 6. But I'm not supposed to leave a negative exponent in my answer, so this goes to the denominator, okay? So that's 36 stays in the numerator because it's not raised to a negative power, over k to the positive 6. Okay, now here I have a negative here. So I could apply that negative 3 to all of these, but it might be easier to go ahead and make that negative exponent positive. So that'd be 1 over negative 4x to the 5th to the 3rd. Okay. Now that third exponent applies to the negative 4 and to the x to the 5th. So that'd be 1 over negative 4 to the 3rd times x to the 5th to the 3rd. Going to work to the right. That'd be 1 over, the negative 4 to the 3rd is negative 4 times negative 4 times negative 4. That's going to be negative 64. And then x to the 5th to the 3rd. You multiply to get x to the 15th. Finally, negatives don't belong in the denominator. A positive divided by a negative overall is a negative. And then 1 over 64x to the 15th would be a good simplified result. Now what about this? I've got a negative in the denominator. Let's handle that negative exponent. That means he can go in the numerator. So the x to the 7th is still in the numerator, but the x to the negative 4 that was in the denominator can get moved to the numerator, but don't forget to change the sign of the exponent. And then remember, when you multiply common bases, you add these exponents together, so x to the 11th is our final answer. Here, now this time, my x to the negative 4, the negative's in the numerator, he belongs in the denominator. The x to the 7th can stay in the denominator because it's already positive. So, okay, if x to the negative 4 goes to the bottom, and x to the 7th is already in the bottom, my question is, what goes in the numerator? Well, it's a 1, right? It's a 1. So this is going to be 1 over x to the 11th power. Compare these two. Make sure you're comfortable with that. Now, at the end of our lecture here, let's talk about scientific notation. You'll see this in a chemistry class and a physics class, and I'm sure in your biologies as well. But it's a way to write a really big number or a very small number a little easier. 2.3 times 10 to the 5th really means you move the decimal place to the right 5 times. Really, you're multiplying 2.3 times, now that's what, 100,000? Because it's a 1 and 5 zeros. But I don't want you to think about those big numbers. This is a direction. That means move the decimal 5 places to the right. Whenever you see 10 to a positive exponent, that means you're dealing with a bigger number than what you're looking at. So if I move the decimal, okay, so right now it's 2.3. If I move it to the right 5 places, it starts here, that's 1, and then 2, 3, 4, 5. Let's think about that. So 1 to get behind the 3, then 2, 3, 4, 5. So in standard form, our number is 230,000. So notice I wrote it exactly. I just put a comma after the right 3 zeros. So 230,000 is standard form, but that's equivalent to 2.3 times 10 to the 5th. Okay, let's try another one. All right, now 2.3 times 10 to the negative 5. Now that's a really small number. If you ever see a negative exponent in scientific notation, that means move the decimal 5 places to the left. Okay, so my decimal is right here right now. If I move it, that's 1 place right there. And then I would move it 2, 3, 4, 5. So you count with me. That's 1, 2, 3, 4, 5 places. So this is equivalent to 0.0000023. Now that's being lazy. If we read this appropriately, remember it's tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. So this is 23 millionths. Okay, but that's much easier. This is much easier to read, 2.3 times 10 to the negative 5. And when you start dealing with really, really big numbers or very, very small numbers like 10 to the 23rd or 10 to the negative 16, it is so much easier to write it in scientific form rather than standard form. Okay, now here we're working opposite. Really big number means a positive exponent, right? So you ask yourself, where is the decimal right now? Okay, so the decimal right now is sitting right here. And we want to move it to past the first non-zero number. So we need to move it right there. So our answer is going to be 1.23 times 10 to the what? Well, it depends on how many times we moved it, right? It's here. So I count 1, 2, 3, 4, 5, 6, 7, okay, and it's a big number, so it's times 10 to the 7th. Now notice I've moved it to the left, but that's the opposite directions of what we have here. So going from scientific notation to standard form, a big number moves it to the right. Well, to go backwards, you move it to the left. So I think it's easier to think big numbers have positive exponents, but decimal numbers or smaller numbers have negative exponents. So again, count again. You don't count where you are. That's 1, 2, 3, 4, 5, 6, 7. So 1.23 times 10 to the 7th. Okay. Now this is a really small number, which means we're going to have a negative exponent. So I can say this is 5.6 times 10 to the, well, to the what? We need to count again. So right here, this is where our decimal is right now. Now if I move it 1 place past this 0, that's 1, 2, 3, 4, 5, 6. Okay, so since it's a small number, that would be 10 to the negative 6. So 5.6 times 10 to the negative 6. The decimal always goes past the first non-zero number. So I don't want to do 12.3, I just want to do 1.23. Okay, so it moved from here to right there. Now, one thing really nifty about scientific notation is you can do calculations with scientific notation. You do not have to change it back to standard form. So if I do this problem, what I'm thinking about right here is I multiply 3.2 times 1.5. So I'm going to do that first. So 3.2 times 1.5 gives me 4.8. So that's 4.8. And then I multiply my 10 to the negative 2 times my 10 to the 7th. Now we know how to do that, right? If you multiply the same base, okay, you keep the base, so times 10, and you add the exponents. Negative 2 plus 7 is to the 5th. So that is 4.8 times 10 to the 5th. All right, now let's do this with division and see how it goes. All right, so when I do division, first of all, I can work with the number part. 8 divided by 2 is 4. Now, I'm dividing 10 to the negative 4 by 10 to the negative 6. Remember, the rule is if you have the same base, you subtract these exponents. All right, so that's going to be times 10, and this is negative 4 minus a negative 6. All right, so think about what's going on. This is negative 4 minus, because you're dividing, a negative 6. So when you work with sign numbers, remember subtraction always changes to addition, and you change the sign of the next number. So keep change, right? So when I combine those together, when I add, that's going to be 4 times 10 to the 2nd power, which is just 400. But in scientific notation, it's 4 times 10 to the 2nd. Okay, hope this helps. You have a wonderful day.